Okay guys, so today we're going to be starting Unit 10, our unit on probability, and we're going to be starting with 10.1, which is to apply the counting principle, and then we're going to be discussing what is called permutations. So our very first example starts with what we call a tree diagram, and I do want you to draw this on there. Okay, so this is called a tree diagram. And the purpose of the tree diagram is to show the different possibilities that our situation can have. So in the situation, we have a sporting goods store that offers 3 types of snowboard: all mountain, freestyle, and carving. And then there's 2 different types of boots. So each type of snowboard can use either a soft boot or a hybrid boot. So our tree diagram starts with our first choice, which is what type of snowboard. So we have all mountain, we have freestyle, and we have carving snowboards. And then we have to branch off of each of those in the different different possibilities of boots. So all mountain, you can have an all mountain snowboard with soft or hybrid boots. So that gives us an option of all mountain board with soft boots or all mountain board with hybrid boots. For freestyle boards, we can also have soft or hybrid boots. So our option is freestyle board with soft boots, freestyle board with hybrid boots. And then the same thing for carving. We can have soft or hybrid boots. So we would either have a carving board with soft boots or a carving board with hybrid boots. So then the question is, how many choices does the store offer for snowboarding equipment? Well, we had 1 choice, 2, 3, 4, 5, 6. So there are 6 different choices for snowboarding equipment. We could also calculate this mathematically because we had 3 different types of board, and then there were 2 different types of boot for each board. So we could also do 3 times 2 equals 6. Okay. And that is what is called the fundamental counting principle. So the fundamental counting principle says that you multiply the number of choices for each decision. So we first had to decide what type of snowboard we wanted, which we had 3 choices, and then we had to decide which type of boot we wanted, and we had 2 different choices. So that gave us a total of 6 choices. So let's look at another example, and this time we're going to do it without the tree diagram. So this example set wants to know, the store in example 1 also offers 3 types of bicycles. We have mountain bikes, racing bikes, and BMX bikes. We also have 3 different wheel sizes: 20 inches, 22 inches, and 24 inches. And then my question is, how many bicycle choices does the store offer? So we know that we're going to use the fundamental counting principle here. So we're going to multiply the number of choices for each decision. So the first decision we have to make is what type of bike we want, either mountain racing or BMX. So we have 3. Then we know we have 3 different choices in wheel: 20, 22, and 24. So we're going to multiply by 3 again, which is the number of choices for our wheel. And that means we have 9 choices for bikes. Let's look at another example that has to do with license plates. Now, you don't have to write the problem down, but I do want you to write down the work. So here's what the problem says. The standard configuration for a Texas license plate is 1 letter, followed by 2 digits, followed by 3 letters. And part A, I want to know how many different license plates are possible if letters and digits can be repeated. So that's the important part here. So the way that we're going to do this is we're going to use the fundamental counting principle, and to kind of illustrate what we're doing and to make it easier for myself, I usually like to put blanks in the number of different options that we have. So we're going to start by one letter. So I'm just going to put a blank there, and I'm going to put an L to indicate it has to be a letter. My next digit is going to be a number, and I'm going to have two numbers there. The next is three letters. So I'm going to put three blanks for each of my letters, and I'm going to label them L. And then this helps us set up our fundamental counting principle. So we're going to put in each one of these an amount of choices we have for each decision. So if my first has to be a letter, we need to look at how many letters that we have possible we can choose from. So there are 26 letters in the alphabet, so we can choose from 26. My next one is a number, and so we're looking at just the single digits going from 0 all the way to 9, so that is 10 numbers to choose from. Then my next entry is also going to be a number that is also 10 digits. Because we can repeat, we can put in the same number, so we still have 10 to choose from, and the same with the letters. So because we can repeat letters, we can use all 26 letters for each one. So then to do the fundamental counting principle, we're going to multiply all of these different choices together. So that is going to give me 45,697,600 different license plate configurations. Now the next part of the question wants to know how many different license plates are possible if digits cannot be repeated, or letters. So for part B, we're going to do the same thing, but our choices are going to be a little bit different. So we're going to still have 6 different choices: a letter, a number, a letter, a letter, and a letter. But our different options are going to be a little bit different. So for our first letter, we still have 26 letters to choose from. Our first number, we still have 10 digits to choose from. But if I use, say, a 5, I can't use it again. So my second number, I only have 9 digits to choose from. Same thing is true with the letters. If I used, say, an L to start, I can't use that same letter again. So I only have 25 letters that I can choose. The next letter is I only have 24 to choose from because I can't repeat. And the last one I only have 23 to choose from because I still can't repeat. So when I multiply all of those together, I end up with less options, but still a lot: 32,292,000 options. So that's the fundamental counting principle. You multiply all of the different choices together. So let's put a definition to this. When a group of objects or people are arranged in a certain order, the order of the objects is very important. That's called a permutation. So a permutation has to do with when you put things in, group them, and the order does make a difference. So we have a formula to calculate these. The way that we read this is permutation of n choose r. So the number of permutations of n objects, so the n is going to be the number of total objects, taken r at a time. So the r is going to be the how many that you put in a group at each time. And we read this as P of n choose r is n, and this exclamation point is a new operation called factorial, and I'll define that for you in just a second. N factorial over n minus r, and then factorial of that. So factorial means that if I take, say, 6 factorial, I'm multiplying everything from 6 all the way down to 1. So 6 times 5 times 4 times 3 times 2 times 1. If I asked you to find 7 factorial, that would be 7 times 6 times 5 times 4 times 3 times 2 times 1. And then whatever the answer comes out to. The one that does differ a little bit is 0 factorial, and I want you to make sure you have this one written down. 0 factorial always comes out to 1. And that's because we can't divide something by 0, and it means that we're only picking one number, so it always comes out to 1. So let's actually do some of these. Now for these examples, they are all word problems, so you don't have to write the word problem, but I do want you to write the work. So let's look at example 3. Example 3 wants to know how many 4-letter patterns can be formed using the letters A, B, C, and D if each letter is only used once. So we're going to be taking the permutation, because if each letter can only be used once, that means the order does matter. And we have our n is going to be 4 because we have 1, 2, 3, 4 letters to choose from. But when we're arranging them, we're putting 4 letters in each arrangement. So we're picking 4 at a time. Okay, that means that each arrangement is going to have 4 letters. So according to our formula, we have n factorial, so 4 factorial, all over n minus r, so 4 minus 4. And then we're going to take factorial of that. So this is going to be 4 factorial is 4 times 3 times 2 times 1 all over. 4 minus 4 is in parentheses, so you have to do that first. So that's going to be over 0 factorial, which we know is 1. 4 times 3 times 2 times 1 gives me 24 over 1. So the amount of letters that I can be, or the amount of patterns that we can use or form is going to be 24 different patterns. So let's look at one where we're not putting the same amount as that we have in each permutation. So I now want to know how many ways 3 books can be placed on a shelf if they are chosen from a selection of 8 different books. So none of the books, we can assume none of the books are the same. So I have 8 to choose from, so my n is 8, but I'm only putting 3 at a time. So that means I'm going to be picking 3 at a time. So this is going to be 8 factorial over n minus r factorial. So that's going to be 8 minus 3 factorial. So let's simplify that first. This is going to be 8 factorial over 5 factorial. So let's write it all out. 8 factorial is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, all over 5 factorial, which is 5 times 4 times 3 times 2 times 1. Now, I would suggest that instead of multiplying all of this out and then multiplying all of that out and dividing, that we reduce here while we can. So if you notice, I have 1's that reduce. I also have 2's that reduce. 3 and 3 reduces, 4 and 4, and 5 and 5. So I'm actually going to be ending up with just 8 times 7 times 6, which comes out to 336. So let's do some more examples. I'm going to have you guys do these on your own. So you're going to want to pause the video for a few minutes and have everybody together in your groups work on 5 permutation 3. Now this is a different type of notation. The first number is your n and the second number is your r. So this is the same as permutation of 5, 3. You will actually probably see it written like this more often than what I had been using previously, but I want you to be used to seeing it in both notations, but these two are exactly the same. So 5 is going to be your n, 3 is going to be your r. So do these, pause the video and do these next 4 problems together. So, number 4, we should have got 5 factorial over 5 minus 3, which is 2 factorial. If we were to write this all out, it would be 5, 4, 3, 2, 1, and the denominator is 2, 1. So we can reduce the 2's and the 1's. So you should have been left with 5 times 4 times 3, which all comes out to 60. The next one should have been 4 factorial over 3 factorial. So 4 factorial would have been 4, 3, 2, 1. 3 factorial is 3, 2, 1. So we are going to just end up with 4. Number 6 would have been 8 factorial over 3 factorial. The 3, 2, 1's will cancel, so we would be left with 8, 7, 6, 5, 4, which all comes out to 6,720. And our last one should have been 12 factorial over 12 minus 7 is 5 factorial. 5, 4, 3, 2, 1 will reduce, so we would be left with 12 times 11 times 10 times 9 times 8 times 7 times 6. So when we multiply all of that out, it would come out to 3,991,680. So we also have a special kind of permutation called a permutation with repetition. So this would happen if we are allowed to do repeats in our permutation. So for example, the number of permutations of n objects of which p are alike and q are alike. So here is your formula for a permutation with a repetition. N is the number of objects that you have, and P and Q are the number of repetitions of particular objects. So for example, and I do want you to write this one, how many ways can the letters from the word Georgetown be arranged? So we want to rearrange the letters in the word Georgetown and see how many we have. So the first thing we're going to do is we're going to count how many letters we have total. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's your n. So this is going to be 10 factorial over. We divide by the number of letters that are being repeated. So we have a G being repeated 1, 2 times. We also have an E being repeated 1, 2 times. And we have an O being repeated 1, 2 times. All the other letters are not being repeated, so we don't have to worry about them. So let's write all of this out. This is going to be 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, over 2 factorial is 2 times 1, times 2 times 1, times 2 times 1. So we wrote them all out. The 1s are all going to reduce with each other because 1 times 1 is still 1. Here we have the 2's that are reducing. And then I am left with a 2 and a 2 on bottom, but 2 times 2 gives me 4, so we can reduce it with the 4. So we're going to be left with 10 times 9 times 8 times 7 times 6 times 5 times 3, and then everything else reduced. So when we multiply all of that out, we are going to get 453,600. And that's your introduction to permutations and using the fundamental counting principle.